So as far as principles of counting, the multiplication principle is exactly that. I wonder, actually, I'm curious now, before I start saying things, I wonder what your book has to say about the multiplication principle. Let's take a look and see. Let's see what the book has to say. So the book in section 12.1. Let's see. Okay, yeah. So here's what the book has to say about the fundamental principle of counting, which is just the multiplication principle. Suppose k selections can be made independently. The first having n1 possible choices, the second having n2 possible choices. Basically, I can't even read the whole thing, it's just, right. And the kth one having nk possible choices. Then taken together, the total number of possible choices is n1 times n2 times n3. So if you have some number of choices you get to make, each independent, and each of those choices has some amount of possibilities, you multiply all those possibilities together to get the total number of possibilities. Let's look at some examples. So I'm going to say some words and I'll write down the important stuff. So in planning your class schedule for next quarter, there are 4 different stats sections. Let's say stats 13 or stats 100. I don't know. Let's say stats 13. And there are 2 different biosci, let's say 1A sections. And there are 3 chem 2B sections, which is unrealistic, right? Because we know there's way more chem 2B sections than 3 sections, but whatever. And there's also 2 intro to dance sections. And I want to know, taking these 4 classes, how many different schedules could I make? Well, we could make a tree, but we don't really need to. So what I want to point out is, right, like, it's just, you're just going to multiply them together, right? You have 4 choices for your stats class, section 1, section 2, section 3, section 4, and you have 2 choices for your bio class, and you have 3 choices for your chem class, and you have 2 choices for your dance class. So multiplying that all together, you get 4 times 2 times 3 times 2. That's going to be what? 8 times 3 is 24 times 2 is 48 different possible schedules. You could make a tree diagram if you wanted to, but it's not really necessary. Right, if you look at like each of the different sections of stats, so for each section of stats, you could pick 2 different sections of bio. 2 different sections of bio, the first section of the second section. And then for each section of bio, you can pick the first section of chem, the second section of chem, or the third section of chem. And then for each possible section of chem, you can pick the first section of dance or the second section of dance. And so you can kind of see, right, for just this first section of stats, there's going to end up being 2, 4, 6, 8, 10, 12 possible different schedules I could come up with. Right, I could do this and this and this and this, or I could do this and this and this and that. Right, so basically every end of your tree diagram is one distinct choice of different classes: stats, biology, chemistry, dance. I don't want to draw them all out because it's kind of a lot, but right, if I drew the rest of these, we'd see that there's 6 here off this branch, and there's 6 here off this branch, and then there's 1, 2, 3 more identical ones, except you're starting with section 2 of stats or section 3 or section 4. So there's 12 sections here, 12 here, 12 here, or so I should say there's 12 course choice patterns here. There's 12 distinct ones here. There's 12 distinct ones here. And there's 12 distinct ones here for a total of 48. Yeah. So the multiplication net principle is pretty straightforward. Let's look at a couple more examples. In a study of the effects of light and fertilizer levels on plant growth, you plan to study 5 different fertilizers. You have 3 light levels. And for each combination, for each fertilizer and light combination, which we notice there are 15 different possible combinations, right? 5 different fertilizers, 3 different light levels for each one type of fertilizer. For each combination, we want to have 4 trials, replicates, I don't know, what do you want to call them? 4 trials. Great, well, that's easy enough. Then the total number of trials, or plants, or whatever you want to call it, fertilizers, total number of replicates is the word used here, is going to be 5 times 3 times 4. 5 different types of fertilizers, 3 types of light, 4 per each type of light and fertilizer. That's going to be 60 total. The multiplication principle is kind of boring, right? Like you're just like, okay, I can have some of this and some of that, some of that. I don't know what else do I want to say. Yeah, sure. He did a 1 topping pizza example in class, which I thought was reasonable. Right? You have like 5 different types of 2 different types of cheese, 3 different types of sauce, and you multiply them all together. Sure. Here's the one that's a little bit more biologically themed. The genome for HIV contains 9,749 nucleotides. There are 4 different types of nucleotides, right? A, C, T. I think, right? My biology is not great. It's been a long time since I took biology, but I believe we're talking about like the A, C, T, and G, although I'm not 100% positive about that. But I feel kind of like I might just be making stuff up. Anyway, contains that many nucleotides, and there are 4 different nucleotides. So the question is, how many genomes are possible? Well, we have 4 choices for the first one. We have 4 choices for the second one. We have 4 choices for the third one, all the way down to 4 choices for the 9,749th one. So we have 4 times 4 times 4 times 4 times 4, 9,749 times. That's going to be 4 to the 9,749th power. Not particularly exciting. But that's kind of the very basic idea about the multiplication principle. You're just saying if you have so many choices for this thing and so many choices for this thing, and you want to know how many possible combinations you have, maybe combinations not the, no, that's, these combinations is the word I want to use. Let me see. Yeah. How many possible things you can have, you multiply the different possibilities for each choice together. So I will state the multiplication principle is pretty straightforward. Let's move along to the second counting principle, which is permutations. And again, I know he said this in class, and I will say it as well. The difference between permutations and combinations is typically the order matters. Now you might be thinking here, well, like for this example I just erased, right? This a permutation or combination? Well, it's more of a combination, right? Because the order you pick the classes in doesn't really matter. Yeah. But again, the multiplication principle is kind of, it's more that we use the multiplication principle when we're talking about either permutations or combinations. So let's talk about permutations. Permutations, where again, order matters. So that's when you are asked a combination or a probability or a combinatorics question, you should ask yourself, in this situation, does the order I'm looking at the things in, does the order matter or not? That's kind of the first thing you want to think about, really. So let's look at this one. At the library, we have 5 different chem books. 5 different chem books. We have 6 biology books. Again, all different. And 4 different math books. how many ways can we arrange the books on the shelf? Well, here order matters because, right, we're arranging them from left to right. And depending on how we put them, it's going to look differently. So if we're asked how many ways you can arrange a thing, typically that means order matters. So in the first spot, well, there are 15 books total. In the first spot, I can choose any 15 of them. But in the second spot, well, I've already chosen one of the books. Maybe I chose a chemistry book to go there. So now there's only 4 chemistry books left to choose from, and there's still the 6 bio books and the 4 math books. So in the next spot, there are 14 books to choose from. And in the next spot, there's 13 books to choose from. And so on and so on and so on, all the way to the last couple spots. That's our total number of choices. That's the total number of ways we can arrange these 15 different books. This number, I know we talked about this in class well, this is more compactly written as 15 factorial. And just a little exclamation point after the 15. That means the same thing as 15 times 14 times 13 all the way down to 1. I will also point out this number is big. Apparently this number is, I feel like this is an approximation. It's 1.31. Yeah, that's probably an approximation. Times 10 to the 12th. It's a big number. There's a lot of different ways you could arrange these books, right? 10 to the 12th is like on the order of 1 trillion. So big number. From just 15 books. A couple things to say about factorials, right? 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is just 1. And I will tell you, we're not going to get too deep into it, but it's important that you know, it might, well, I should say, it might be important that you know that 0 factorial is equal to 1. It's kind of like how anything to the 0th power also equals 1. It's really because the way our mathematical systems are set up, we need 2 to the 0 to equal 1, right? Because we need 2 to the 0 times 2 to the 3rd to equal 2 to the 0 plus 3, which is 2 to the 3rd, right? The additive law of exponents. Well, if 2 to the 0 times a thing is equal to the same thing, that has to be 1. There's a similar argument, which I will maybe show you guys later, about why 0 factorial has to equal 1. It's not hard to get, we just aren't out there yet. Okay. The other question I want to ask is, what if all the books of the same type have to be grouped together? Now, this is a more interesting question. So if I want to group all the same types of books together, I can either do, well, I can do the 4 math books, and then I can do the 6 biology books. Not really. And then I can do the 5 chem books. Okay, now, let me ask you guys, and I would actually like some responses in the chat, which I just closed because I'm super smart. Let me open the chat again. How many ways can I arrange the 4 math books if they all have to be next to each other? You can answer this by typing 2 things. Right. You also could have typed 24 because 4 factorial is equal to 24. How many ways are there rearranging the biology books? Well, there were 6 of them, so. And the chemistry books, there are 5 factorial ways of arranging them. Now here's the thing, we're not done. Because while there are, right, if you want all the math books next to each other and all the bio books next to each other and all the chem books next to each other, these are the ways you can arrange each of the books in themselves. But who says math has to be first? Who says bio has to be second? Who says chem has to be third? So the other thing we have to multiply by is how many ways can you actually decide which thing goes first? I could do math, bio, chem. I could do math, chem, bio. I could do bio, math, chem. I could do bio, chem, math. I could do chem. Oh, there's 3 factorial ways, right? There are 3 things, 3 subjects here I'm arranging, and I can pick any one of them to be first, any one of them to be second, anyone to be third. So there's 3 choices for the one that goes first, times 2 choices for the one that goes second, times 1 choice for the thing that goes third, or 3 factorial. So this would be whatever that number is. I will also mention, most of the time, we don't actually care what the number actually is. Meaning, nobody wants you to actually multiply this out. This is the answer you should give on a test. This is the answer you should give in web work. Unless someone specifically says multiply the damn thing out, don't. Just leave it as this times this times this times this. Maybe with some parentheses just to be extra careful. But yeah, really, really, like, when he was in class today and someone asked him like what's 4 to the, I don't remember what power it was like 4 to the, I don't know, 13th power or something. Nobody cares. Nobody really, I mean, somebody cares at some point, but like, as far as these math questions go, they want you to be able to express the answer, knowing the actual number, not super important, usually. Okay, often in combinatorics problems, what do I call the method I did in the box? Permutation in category? That's a good question. So I will say a lot of these combinatorics problems require, I don't know if common sense is the right word, but some sort of, it requires some level of math sense. So in the box here, right, like I was like, so it definitely is still permutations, right? So first, so again, remember the question was, how many ways can I arrange the books so that all the math books, all the bio books, and all the chem books are next to each other? So first I just said, well, I have to group all of the things. So I can have all math, or all bio, or all chem. And then I talked about the ways I could arrange the math and the bio and the chem. But then I also said, but I can also think about the number of ways I can arrange the different categories. So yeah, you could say it's permutation in category, right? I can rearrange these in 6 different ways, or 3 factorial different ways. So sometimes you kind of have to, there's a lot of kind of just thinking about like, okay, how many ways can this really work? And it can be, sometimes kind of dicey. What I was gonna say is a lot of questions we ask in combinatorics about are how many different words you can make, where words usually don't spell anything. So how many words can you make with the letters from the word math? Well, if I can arrange them anyway, I can have, you know, M-T-A-H, I could have M-H-A-T, I could have T-A-H, right? There's a lot of possibilities. I don't want to write them all out. So what I'm going to do is I'm just going to make a little, often we make these little kind of pictures where you talk about what can go in each place. So in a 4-letter word, all letters are different. I have 4 choices for the first letter, 3 choices for the second, 2 choices for the third, and 1 choice for the fourth. So the number of quote unquote words is 4 factorial. And honestly, even though I know 4 factorial is equal to 24, I feel like writing down 4 factorial better expresses your understanding of the question. You're like, oh, I know it's 4 factorial. So you 4 times 2 times 2 times 1. I don't need to write that it's 24. This shows that you got it. What if the word was instead data? Okay, note that in data, this A and this A look exactly the same. I'm assuming you wrote them the same, right? There's no difference between them. So what I want to point out is if we call this, like if this is the first A and this is the second A, this word looks the same as this word, even though the letters are arranged differently, right? A1 is here, A2 is here. Hopefully you guys can see the 1 and the 2. So the idea here is that we're still going to have the number of words, well, there's still 4 times 3 times 2 times 1 choices, but for all 24 of the words we're going to get, we're actually double counting, right? right, if I have the word, DAAT, and I'm talking about all 24 possibilities, that's going to show up twice. It's going to show up once as DA1A2T, and it's going to show up again as DA2A1T. So every word that's showing up is actually showing up twice. So I have to divide by 2 factorial, which is the number of arrangements of the A's in each word, right? For any word, there are 2 factorial ways you can arrange the A's. You can put A1 here and A2 there, or you can flip them and put A2 here and A1 there. So basically, when you have a letter that's repeated, you have to divide by the number of times it's repeated factorial to account for all the possibilities. I feel like, even though I don't want to do it, it might be useful to actually write them all out. So let me show you what I mean by this, in case anyone's really unclear on this. So here are the 12 distinct words. So you have D, A, T, D, A, T, A, D, T, A. Those are all the distinct words with D in front, I think. Sounds right. So let's now put T in front. You have T, A, A, D, T, A, D, A, T, D, A, A. Okay, and then we put an A in front. You can have A, D, A, T, A, D, T, A, A, T, D, A, T, D, A. Now here's the thing. If you said there were 4 factorial possible words, that'd be correct, because, right, this DAAT would be different than this DAAT. I don't want to write them all out, but right, essentially what I'm saying is each of these words would actually show up twice, right? Where you have A1, A2, and then you have A2, A1. And so I don't want to double count, right? I only want to count words that actually look different. And DAAT looks the same as DAAT. And so what I'm doing is I'm taking my 24 possible words, right? I didn't write the other 12 of them over here. I take my 24 possible words and I divide by the number of ways you can rearrange the A's in any word. So hopefully that makes it a little more explicit as to why we would do that, because you really only get 12 distinct words here. Yeah. I like this pen. I feel like my orange pens are not excellent. Like I have all these orange pens and they don't really kind of just. Which I mean, I would agree with because I don't like the orange pens anyway, but yeah. So this principle holds for kind of any arrangement of letters. Classic example, Mississippi. M-I-double-S-I-double-S-I-double-P-I. Okay. So how many words can you make with the letters of Mississippi? Well, first of all, how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 letters. So there's 11 factorial ways we could arrange them. But there are 4 S's. So there are 4 factorial ways that we could arrange the S's. So basically, if you said you had 11 factorial words, for every one word you have, there are 24 different ways. Basically, there are 24 different ways you could rearrange the S's here and still get the same word. So I don't want to count all 24 Mississippis. I just want to count one of them. So I'm dividing by 24. And then there's also 1, 2, 3, 4 I's. So I'm divided by 4 factorial to account for the 24 different ways I could rearrange all the I's. And then there are 2 P's. So I'm divided by 2 factorial as well. There's also a 1M. You don't need to divide by 1 factorial because 1 factorial is just 1. So there are 11 factorial divided by 4 factorial, 4 factorial, 2 factorial ways of arranging distinctly the letters in the word Mississippi. Okay. So another example. In an art contest, not a contest of people named Art, but a contest about drawing pictures. An art contest, not a contest of arts. With 10 entries. I mean, I guess it could be a contest of people named Art. That would also be fine. Interesting piece of information. Apparently, I don't remember the name. I think the name was Josh. I think there was a gathering of many Joshes. I think it was Josh in some part of the world, and they all had like a giant foam sword kind of fight to decide who could be the one Josh. I think it was Josh, but it sounds like it was probably very entertaining. Anyway, not important. So art contest with 10 entries. How many ways to award the top 3 prizes? All right, well, there's 10 choices for the first place. And there's 9 choices after you've chosen someone for the first place for the second place. And then there are 8 choices for the third place. And that's it. We're done. 10 times 9 times 8, that's 720 different possible ways you could choose 3, a first, second, and third prize from 10 people. So we have this formula for permutations. Again, permutations order matters. So the number of permutations of k objects chosen from n objects is given by, sometimes people use this notation, P of n comma k. A lot of calculators have it written as NPK, or probably NPC, actually, I think is the, no, I think they use K. Where's my calculator? Let's have my calculator. No, they use R, okay. K or R. I'm sorry, that could also be an R if you prefer. It's n factorial divided by n minus k factorial. Or if it was R, it would be n factorial divided by n minus r factorial. In this previous example, right, you want a number of permutations of 3 things chosen from 10 things. It's exactly 10 factorial divided by 10 minus 3, which is 7 factorial. So that's 10 factorial divided by 7 factorial, which you could leave that way, but then you'd be like, oh yeah, that's right. Everything after this, the 8's going to cancel. You have 10 times 9 times 8 times 7 factorial divided by 7 factorial. And these cancel out. So you get the same thing. See, what time is it? Okay, we got time. We got time. So a security code, a PIN, if you will, is formed by any arrangement of first 4 different letters, followed by 3 different numbers. Okay, how many different codes could you make? Well, you can make one that was like A, B, C, D, 273, or H, I, Q, that's not a Q, that's a K, H, I, K, Q, 916. The list goes on for a while. The way we can calculate this is it would be, well, first I have 4 different letters. So how many letters are there to choose from? There's 26. There's a nice thing about letters. There's 26 letters, specifically with cards. So if you know things about a deck of cards, there are 52 cards in the deck. which is exactly twice the number of letters in the alphabet. So that's kind of a nice thing to remember. It's sometimes useful. So 4 different letters, there's 26 permutations. Sorry, not 26. There are, out of 26 letters, we're going to choose 4 of them. This will be the number of permutations we get, times 3 different numbers. There are how many numbers to choose from? There are 10, right? If you count 0 is also a number. There are 10 different digits, I suppose I should say, instead of numbers. So that out of the 10 digits, we're going to choose 3 of them. So that's going to equal 26 factorial over 26 minus 4, which is 22 factorial, times 10 factorial over 10 minus 3. If you want to write this out, I don't think it's really nicer. You could write this out as 26 times 25 times 24 times 23, right? Because that's 26 over 22 factorial, times 10 times 9 times 8. What if instead we said that the letters didn't have to be different? We can have any 4 letters and then any 3 digits. So then you could have a passcode that was like A000. So in this case, we're just going to use the multiplication principle. There are 26 choices for my first letter, and there's no reason to not still have 26 choices for my second letter. So I have 26 times 26 times 26 times 26 for the 4 letters, and then 10 times 10 times 10 for the 3 digits, which I would write as 26 to the 4th times 10 cubed. So having to have things be different versus allowing for repetition does make a difference in how the question works. Okay. So talk about combinations. I'm at the Pizza Hut. I'm at the Taco Bell. I'm at the combination Pizza Hut. Whenever I say the word combination, I think of the combination Pizza Hut and Taco Bell song, which if you haven't heard, you're really missing out. It's a gem. So how many permutations? So how many permutations of 3 letters from the first 5 letters alphabet, A, B, C, D? Well, we already know the answer. I'm going to show it, but the answer would be 5 factorial divided by 5 minus 3 factorial, right, which is your P of 5, which is 5 times 4 times 3, which is 60. I don't want to write them all out, but I do want to show you. So, all right, we could have ABC, ACB, sorry, no more A first. Right, order matters. BAC, BCA, and then CAB, CBA. And then basically for any other 3 different letters, we could have the same kind of 6 ways of ordering them. So right, we could have ABD, and there are going to be 6 ways of doing that. Or we could have ABE, and there's 6 ways of doing that. Or you could have ACD, there's 6 ways of doing that. You could have ACE, there's 6 ways of doing that. You could have ADE, 6 ways of doing that. And then you could have BCD, 6 ways of doing that. BCE, 6 ways of ordering those. BDE, 6 ways of ordering those, and finally CDE. In case you're wondering how I thought about writing this out so I didn't miss anything, I started with ABC, and then I let the last letter kind of tick down. So I said C goes to D, and then D goes to E. I got all the way, and then I let the next one tick down 1 and moved the last one back. So I did ACD, and then let that tick down to ACE. And then finally, I let the C tick down to D, so I get ADE. these are the last letters, so then I have to let the A tick down and start the process over. So then I have B, C, D, and then tick the D down to E, and then at the end, so then I take the C down to D, and that's the last one I can get. And then actually that's the last one I can get. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 6 for a total of 60 permutations of 3 letters for A, B, C, D, E. Now let me ask you guys, how many combinations of 3 letters from A, B, C, D, E are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, there are 10 different possible combinations where order doesn't matter, right? Because all of these are the same as that if order doesn't matter. And all of these are the same as that if order doesn't matter, and so on and so on and so on. So for this problem, the number of combinations of 3 letters from the 5 letters A, B, C, D, E. It's essentially, here's the way it works. It's essentially the number of permutations divided by the number of ways you can reorder however many things you have. So it's going to be the number of permutations, P of 5 comma 3, divided by 3 factorial, which is 6. Right, that's going to be 5 factorial divided by 5 minus 3 factorial, and also divided by 3 factorial, which ends up being 5 factorial is 120, 2 factorial is 2, 3 factorial is 6, 120 divided by 12 is 10. Just like we said it was, right? 10 different ways to do it. 10. So number of commutations. So you could think of the number of combinations of, so I should write it out, sorry. So the number of combinations, Pizza Hut, Taco Bell, number of combinations of K objects chosen from N objects is, and there's like 3 different notations for this. You can write it as C of N comma K. You can write it as NCK or NCR like your calculator does. Or you can write it using my preferred notation and probably Tim's preferred notation as well. Sorry, Professor Lewis, Tim. And choose K. That's the pretty standard mathematical way to do it. And it's equal to N factorial divided by N minus K factorial times K factorial, which is really just the number of permutations divided by the number of ways to order the things that you are permuting. Right, so basically you're taking all the different ways you can order things and saying, well, I don't actually want to count all the ways I can order. I want to divide by the number of ways each possibility gets ordered. So that's why we're dividing here by 6 to get rid of all the repeat counts. I don't want to count all 6 of these and all 6 of these and all 6 of these. I want to count one of those, one of those, and one of those. So I divide everything by 6 to get just 1 instead of 6 of them, or to get 10 instead of 60 of them. All right, now let's see what else have we got here in the last 5 minutes of class. So, how many ways can we form a committee of 3 people out of 7? Okay, well, so if I have a committee of 3 from 7 people, well, the fast answer is 7 choose 3, which again is 7 factorial divided by 7 minus 3 factorial times 3 factorial, which is 7 factorial over 4 factorial times 3 factorial. And you could leave it like this. We probably should simplify a little bit. Let's multiply it. So here's the thing. I'm going to look at the thing on top and the bigger thing on the bottom. So 4 factorial is the bigger thing. I know 7 factorial over 4 factorial is going to simplify to 7 times 6 times 5, because the 4 factorial on top is going to cancel with the 4 factorial on the bottom. That's 7 times 6 times 5, but then I still have the 3 factorial on the bottom, which is 3 times 2 times 1. But 3 times 2 times 1 is 6. So 6 cancels the 3 times 2 times 1. And you get 35. 35 different ways that you could have a committee of 3 people out of 7. Okay. What if two people can't stand each other? Can't both be on the committee. It's a good question. So, yeah, interesting. I did not think of it that way. Sure. So there's two totally, and this is actually true in general. There are often many correct ways of arriving at the same answer. I'm going to show you the long way to kind of help you appreciate that there's a short way. So if I said two people can't be on the same committee, let's call them persons A and B. So I have persons A and B, and then I have the other 5 people, 1, 2, 3, 4, 5. So I can't have A and B together, but I can have B and any 2 of these people. So how many ways are choosing 2 people out of 5 people? Oh, there's 5 choose 2. I could also have, so I don't really need the B there, right? So there's 5 choose 2 committees that have B on them. So B is on the committee. There's also 5 choose 2 committees that have A on them. Right? You can choose A and any 2 of these people. But then you can also have committees where you don't have either of these idiots that can't stand each other, right? You'd be like, from these 5 people, I'm going to choose 3. Let's figure out what we've got. Now, the interesting thing here is that 5 choose 2 and 5 choose 3 are actually equal to each other. Because if you're saying, I want to find the number of ways to choose 2 people on the committee, you could also phrase it as, I want to find the number of ways of choosing 3 people who aren't on the committee out of these 5. So 5 choose 2 is 5 factorial over 3 factorial times 2 factorial. 5 choose 2 is the same. I'm just multiplying this by 2. And then 5 choose 3 is 5 factorial over 2 factorial times 3 factorial. Oh, that's the same as that. So I really got 3 times 5 factorial, which is 5 times 4 times 3 times 2 times 1 cancels the 3 factorial over 2 factorial. So I have 20 divided by 2, which is 10, by 2 factorial is equal to 2, and 3 times 10 is 30. However, there's another way of thinking about this, which is equally valid. So another way I can think about this is, well, I already know that there's 35 committees that can make that have any 3 people on them. 35 different committees with 3 people. I want to eliminate the however many committees have person A and B. So there's 35 total ways, and I want to subtract how many ways I get A and B. Well, if I'm making a 3-person committee, I could have A and B in 1, or A and B in person 2, or A and B in person 3, or A and B in person 4. So there's 5 ways I can do that, right? There's the set containing AB1, AB2, AB3, AB4, AB5. I'm taking my 35 total committees of 3 people out of 7, and I'm subtracting off the 5 that I don't want because persons A and B don't like each other. Well, 35 minus 5 is also 30. How about that? So sometimes there are easier ways to figure something out. A prime example of this is, and I'm sure we'll see this, someone will ask you a question like, if I flip, sure, here's an excellent example. If I flip 5 coins, how many ways can they get at least 1 head? So how many ways? So then you have to count the ways you get 1 head, or 2 heads, or 3 heads, or 4 heads, or 5 heads. Oh yeah, thanks, Janelle. I do appreciate you asking me about screenshotting the attendance because I often forget to. And not that I don't get you guys, but then I have to go back and like look at the Zoom log, and it's if I screenshot the attendance, it's much nicer because you're in alphabetical order. Okay, you're good to go. So you're welcome to go. I just want to say one last thing though. but you can go if you need to go. That instead of counting like the number of ways to getting one head or two heads or three heads or four heads or five heads, if you flip 5 coins, you can instead say, well, I can take the total number of ways of flipping 5 coins, which we'll learn shortly is 2 to the 5th power, right? 2 choices times 2 choices times 2 choices times 2 choices and 2 choices, and then subtract off the one way of getting no heads, which is all tails. So it's really easy to see that the number of ways of getting at least one head is the total number of ways of flipping 5 coins, which is 2 to the 5th, minus the one way of getting no heads, which is all tails. So if you flip 5 coins, there are 31 ways of getting at least one head. And there's one way of getting no heads.